Alright, in this video I'll be going through the answers for the review that I gave you for the final in class, and I'm going to run through it pretty quickly because I really want to focus on the things that you need to be prepared to do on the final. And I'm actually making, I literally gave you a different version than what I intended to. In these last 5 problems, it's a little bit different on your version than the updated version. So I'm doing a separate video on that where I go through more of the details. But hopefully this will be enough if you've already done these problems. So in both videos, you'll see 46. I'm just going to look through it pretty quickly here. Basically, we're using Gaussian elimination with back substitution. Here it's talking about Gauss-Jordan elimination. That's where you not only get ones on the main diagonal and zeros below, but also zeros above the ones. That's what we call reduced row echelon form. But what we had learned was using back substitution once you get it into this Gaussian elimination form. And so basically you start with the matrix that's equal to the original system, and you're trying to work towards getting this desired form here. And so the first thing I did is I needed to get a 1 here. Now this was a little bit tricky compared to some of the other ones we did, but you'll notice if you basically multiplied the second equation by -1, if you add that to equation 1, equation 2 times -1, that'd be -2 plus 3, you would get the 1 that you want. So I did -1 times row 2, and I added that to row 1, and that gave me the new row 1, and so you get 1, 5, 15. So row 2 doesn't change going from here to here. And then now that we have the 1 in the upper left hand corner that we want, and that's where we always start with getting the 1 in the upper left hand corner, we want to use that 1 to get a 0 below. And so since that's a 2 in row 2, I want to multiply the first row by -2 and add that row to row 2. So -2 times row 1 added to row 2, that's the new row 2. And so row 1 didn't change. Basically I did -2 times 1 plus 2 is 0. -2 times 5 is -10. Plus 3 is -13. And this is a 3, it's a little bit hard to see. And then -2 times 15 is -30, added to -9 is -39. And so we get 1, 5, 15, 0, -13, -39. And now that we've got the 1 in the upper left-hand corner and the 0 below, we're going to move down the main diagonal to the next number, and that needs to be a 1. The easiest way to get a 1 there is just divide by -13. And notice the other number is also divisible by 13, so that works out nice. So we don't normally write that as division by -13. We would multiply by the reciprocal, -1/13, times row 2, and that's the new row 2. And so we finally get the form we want, and we take it to equation form. So 1x plus 5y is 15. And 0x plus 1y is 3. So these are my two equations here. We can replace the y in the first equation with 3 and solve for x, and when you do that you get 0. So 0, 3 is the solution there. Now if we had continued going on, which we didn't do this semester, we would have got a 0 above this 1, and that's what happens if you take it all the way to reduced row echelon form, which is what your calculator would do, or the way that we were doing it. So you would start with the original matrix and putting it in reduced row echelon form, it would give you this. You should be able to do the row operations the way we did here, but you should also be able to check it on your calculator and know that you did it right. All right, let's look at 47. It says, what's the goal you're trying to achieve with Gauss-Jordan elimination if you start with this matrix? So again, when we do our row operations to get it into the desired form, we always want to first get a 1 Notice, first of all, I did write this in matrix form, but we always want to get a 1 to start in the upper left-hand corner. Well, we already have that. So the next thing we want to do is get zeros below. And so we would multiply row 1 by -2 and add that to row 2, and that would be our new row 2. We're going to multiply the first row by -3 and add that to the third row, and that'll become the new row 3. So notice it didn't actually ask us to solve this system, it just wanted to know the process. And of course, we're trying to get to the form where we have 1s on the main diagonal, zeros below the 1s, and numbers elsewhere. And then once we do that, we use back substitution. All right, let's move on to number 48. Now, one of the things I changed is I didn't have you actually solve a system where you ran into a special case. And you don't see that on the final either. But you need to know how to interpret the answers. So here on 48, you end up getting a row of zeros. If you write this matrix, or this matrix in equation form, you get this system here. And so basically you have x plus 3y plus z equals -1, and y plus 1/2 z equals -1/2, and that's it. And because you have a row of zeros, you know that you're going to have infinitely many solutions. It's just we need to be more specific than that. We should be able to write out their form. What do points look like if they're solutions to this system? And so first of all, you should know that there's infinitely many solutions, but you should be able to use these two equations to actually write the form of a solution. And so basically, notice the second equation can be solved for y pretty easily in terms of z. So if we let z be our parameter, that's what I did here, then the second equation we solve for y, and we get y equals -1/2 z minus 1/2. And so that's y in terms of z. Now to find x, I had to replace y with what we just got. Now notice I didn't have to do anything with z because z was called z. And so y is in terms of z, but for z, that's just z. So when we solve this, we get our x value. And so that would be the way we would write our solutions in general. Now the other case, in terms of special cases, is when you get to the last step and you get an equation like this: 0x plus 0y plus 0z equals -20. Well, that's telling me that 0 equals -20. Well, that's a false statement, which tells me there's no solution. This is the case where it turns out two of the planes are actually parallel, and that's why there's no solution. There is no common point of intersection for the three planes. All right, so that's the special cases. Let's move on to 49. Actually, I'm going to pull this down just a little bit. And what I've done here is I've translated the word problem into the three equations, and then I've made a matrix and used that matrix to solve the problem, which is what we did in class. This is not the best example, and that's one reason why I changed the last 5 problems, or at least last 4 problems on the review. So, you know, it doesn't hurt to do this problem, but it's not as good a preparation as the other problem you'll see on the other version. But also in section, it was 3.4 and 3.6 we did word problems, and on the second page there were 3 word problems for 3 equations and 3 variables. The first 2 on that page are also good examples to look at as you prepare for the final. And again, with 50, I would encourage you to look at the first page of that assignment for section 3.4 and 3.6. But it's not that this isn't good practice, but I think there were some better problems there. And also you'll see the example that I picked on the other version of the review. And so you can check your answers here, but again, I don't think these are the best problems to prepare for the final. All right, so I would encourage you to watch that other video and at least go through it and just make sure you understand the main concepts there. Maybe practice the other problems that are there that are different. If you have any questions, let me know. All right, that's it.